is. Okay. Uh, this is our Flexure Lab Presentation report. I'm Mariela Abielias.
I'm Janady Ruiz.
Okay. So to start, in our experiment, we did a 3-point bend test of a sample of polycarbonate, and then we took our data to find the Young's modulus. The Young's modulus is the ratio of the stress and strain of a material. Stress is the force acting on that material over a certain area, and strain is the ratio of the change in length over the original length of the sample. And we want to find out how accurately we can determine a material's Young modulus using 3-point bend tests. To set up the sample, we measure the sample's width, length, and thickness. And then after taking those measurements, we marked the center of the sample with like a sharp object. And then on the other side, we sanded that area of the sample and cleaned it up. We then took the strain gauge and placed the wire on the sand and placed on the sanded side of the sample and taped the wire to it. We then removed the film from the strain gauge and placed adhesive onto the center of the sample and pressed the gauge onto the adhesive until it was stuck on the sample. From there, we removed the tape and attached and then stripped the wires of the strain gauge to connect them to the screws on the force loader.
We then placed the sample onto rollers, measured the gauge length, which is the length between the rollers, read the rest voltage from the voltmeter in millivolts. We had zero displacement and force gauges. We recorded a video showing all three gauges, force, displacement, and voltage, and then applied force to the sample. We collected the force displacement and voltage data in the video and then put it into Excel. The stress and strain values were found by taking measured values and plugging it into the given equations. The beam deflection graph created by making the x-axis certain values of gauge length and plugging each value into the equation for the y-axis value. Uh, ED was found by plugging slope of force versus displacement into the equation. ESG was found by using the slope of the stress strain curve.
And here you can see our force versus displacement graph. It's a linear correlation. We then took the slope of 42.107 and we plugged it into the equation for Young's modulus, which is stress over strain. Afterwards, or our next graph here shows the stress strain curve we obtained from the strain data gathered from the voltage measurements. And we calculated a slope of 124,432 psi. This graph right here is supposed to represent the beam's deflection or deformation while it was under the maximum load. So for the first half of the values, we just took the gauge length and took fractions of it and plotted it. And then we did the same for the other side. And this table on the right is contains both of our Young's modulus values, and then the right column contains a reference value from a source online that we compared each value to.
For the Young's modulus, it was quite close to the literature value, the one using the displacement, but the Young's modulus using the strain that was given by the voltage was not quite as accurate. The shape of the curve on the deformation graph closely matched the shape observed during the bending test. And figure 5 shows a photo of the beam deformation under the maximum force. The Young's modulus given by the deformation being more accurate than the Young's modulus given by the voltage implies that using force and displacement data yields a more accurate Young's modulus than using voltage data to find stress and strain. Discrepancies could have come from the voltmeter readings affecting the strain calculations. The average rest voltage calculated might not have been constant in the reality of the test. Same thing for the red strain voltage values at each point. Force and displacement data give more accurate Young's modulus values when testing materials. We should opt for this instead of the voltage setup.
In conclusion, the force and displacement data gained from the 3-point bend test provided us with a more accurate Young's modulus for the material. Our 3-point bend test voltage readings did not provide us with the most accurate Young's modulus value. The ability to accurately graph the deformation of the sample under the 3-point bend test also reduces the need to collect voltage data from the 3-point bend test, as you can see how accurately the sample deforms. This is significant because collecting voltage data is time consuming with the setup of the strain gauge and the wire and zeroing everything and making sure the voltmeters in the correct units. If we were to just use force and displacement data instead, we'd spend less time and resources on finding our samples with Young modulus. And this is important because often as engineers, when we're given projects and products to make, we have budget and time constraints. So it's important for us to be able to prioritize our time wisely to find information that we need as quick as possible.
For future work, some recommendations would be after recording to leave the sample under maximum load to take better quality photos of the deformation. And we could use different material samples to see if accuracy discrepancies are constant across different materials.
Here is our reference for the literature value. Thank you.
Thank you.